All right, we're going to go through the experiment that we did that was testing Newton's second law on a modified Atwood's machine, which is this pulley system that's seen right here. So first thing you want to do is make sure you read this carefully. So if you haven't had a chance to read this carefully, please do so now. So for part A, we want to draw the force diagram for the system. So it's important to define what qualifies as the system. And you can see here from looking at it that I've highlighted what qualifies as a system, and really it's everything that is accelerating with our acceleration. Like what's the object that's moving collectively? So for example, this cart is moving with the acceleration that we're seeing. The string is attached to that as well as to this M2, this hanging one. So those are the things that are moving, and the string doesn't technically have mass in this problem, so it's really just a two-object system, but we have to include the string since it's what's connecting those two. So in doing that, when we do a force diagram, I really don't care that much about these red ones for now if I'm just trying to analyze the line of motion, which is this line of motion that it moves along as defined by the acceleration. So this is really the axis that we could normally define as like the x-axis, but this pulley is going to bend that forward axis so that now what was to the right for the car is pointing down for the hanging mass. So that dotted line represents our axis, which gets bent around the pulley. And that was what that reminder was up in the top corner. So now, why is there no tension here? There is a point of contact right here for the cart, but that's touching the string. And since our cart and the string and the hanging mass are our system, that's our object, then this would be embedded within that system. It's internal. So I don't need to include it. If you want to know the definition for this, the proof for this, then although there is technically a tension force that's going this way, there's also a tension force that's going this way. And so if this one's in the positive forward direction and this one's in the negative forward direction, then those would cancel each other out when we consider all the objects together. So if we try to look at the Newton's second law expression for this line of motion, our forward axis defined by the acceleration, then really the only force I have acting is that hanging mass's weight that we could get by doing its mass in kilograms times g. So if that's the only force, this is our net force. We could set that equal to ma, and our mass would be the entire mass of the system since that's what we're analyzing. It's what's highlighted here, and that's our expression. So it's that downward weight of the hanging mass, m2g, that's pulling the entire system with an acceleration a. It's now asking us to separate these two objects and to draw a free body diagram, one for the cart and then two for the hanging mass, but it wants us to do that with the relative magnitudes of those forces shown with the grid, meaning the number of squares that we use as the length for the arrows represents qualitatively how strong it is. That way we can compare some forces that are either equal with the same number of boxes or if one's bigger or smaller. So what's important to do here when you get these grid problems where we're doing that relative magnitude is to create a working copy off to the side. And so if I just draw one off to the side here, I can just use the baseline. I would have a normal force that's acting up on the cart. I would have its downward force gravity, and then we know that there's that tension that's going this way. And this is for the cart. For the hanging mass, we would have tension that's acting up, and its gravity is acting down. And so now when we draw these, we have to be thinking which one's bigger. So going back to the cart here, tension clearly is bigger, so it doesn't really matter what I'm using for that length. So I can just do two boxes there. And with the normal force and gravity, I got to make sure those are balanced. So I can do one box, I can do two boxes, three boxes, but they need to have the same number of boxes. For the cart, I see that I have the tension, and it's that same tension. So I got to make sure, since I made the tension two boxes here, that I do two boxes here. That I have to do. Because it's the same tension. That's why they cancel each other out when I treat it as a system. So now the M2G, notice how we always figure out which one's bigger is by looking to the acceleration. So the acceleration being this way is going to define the positive direction as being down for the hanging mass, and that would mean the M2G has to be larger. So I have to make this more than 2 boxes, so I'm going to go ahead and just make that 3 boxes then to show that it's longer than tension. If we turn these into equations then, we would be writing tension is equal to, since this is only looking at the cart, it's just M1A. Since M2G for this one is the larger force, then I'm going to let that be positive minus that tension. And since we're looking at the hanging mass, then I'm going to use M2 times A. The other equation for the vertical forces would just say that the normal force is equal to M1G. And these are all of the force expressions that we have for this problem. So on the second page here, let's make sure we read this and understand the problem. We can go ahead and describe an experimental procedure. This one you can talk out, you can paraphrase, or you can write. So let's pause here for a second. So now I've cut and pasted in an example of how I describe the experimental procedure, but I do want to make sure that we have read this problem, because I think when we were doing this in class, at least I made this video to help out with people understanding what's going on in this. I don't know if we really read the experiment very closely, so let's go back to that and make sure that we have done that. In this problem, it's saying that this mass is on a level frictionless track and connected to a massless and frictionless pulley, and the other end of the string is then connected to a hanger of mass M2, which hangs vertically. The disc-shaped slotted masses, each with known masses, can be placed on both the cart and the hanger so that we can vary the masses M1 and M2. The total number of slotted masses must remain the same so the system mass can remain constant. So any slotted masses added to the cart must be taken from the hanger's slotted masses and vice versa. So if we try to change M1 by removing slotted masses, then we would have to be placing those that we remove on the hanger, and vice versa. If we remove slotted masses from the hanger, we'd have to place them back in the cart. That was a very commonly overlooked detail. So now that we're doing this experiment, it's saying a group of students want to use this setup, and they want to analyze the acceleration due to various amounts of net force acting on the system. They have a collection of slotted masses with known masses and a motion sensor that's built into the car that can measure the position time and the velocity time data. So when we describe the experimental procedure that would allow us to create a graph of that net force versus the acceleration, we want to then say, like, what are we going to be doing to accomplish this? Okay, so I'm going to choose a fixed number of slotted masses. I think in the experiment I gave you 5. And we distribute them among the cart and the hanger. We would position a motion sensor in front of the car, probably on its back end, not on the pulley side, obviously. And for this one, I'm just saying that let's start with all the slotted masses on one or the other. So I just said let's start with all of them on the cart. And then we collect data with the motion sensor after releasing the system. The motion sensor was going to allow us to get a velocity time graph, which would be the easiest thing for us to obtain the acceleration value for that trial by getting the slope of that velocity time graph. I would then want to repeat this. I would remove a slotted mass from the cart and then place it on a hanging mass to keep that system mass constant, and then repeat this data collection process that we said in 4 through 6 until we've gone through removing all of the slotted masses from the cart to the hanging mass. It's also here to note that if the acceleration is too large, then we would have to stop at that point if we can't accurately measure its acceleration. So I want to point out here that the underlying equation that we're going to be using is actually this equation that we have from this part here, right? This is our net force. So this is going to be my dependent variable. We measured the acceleration and varied this. So this is going to be my independent variable, which means that this is going to be my slope. If I double check this, then I can see that I have constants here with M1 plus M2, although I'm changing M1 and M2 because I need to change M2 to change the net force. Notice that the sum of M1 plus M2 remains constant and therefore should be the quantity that we are getting when we find the slope. So let's go back to the data collection process here. So we need to be getting the net force values. This would be M2G, and that's in newtons. And we're going to be then getting the acceleration, and that's in meters per second squared. So I gave you 5 slotted masses, so we're going to have 5 different trials for this. And I'll jump over to the solution so we can take a look at it. So if I'm walking you through the data process, then what I would be doing is I would be having the mass 2. I got to make sure I have those grams because they may, let's say it's 100 grams. That's actually 0.1 kilograms, right? Because 100 grams is only 0.1 kilograms. So we got to make sure we get it into kilograms and then multiply it by 9.8. So these are just some random values that we have. And then for each of those values, I got a velocity time graph from the motion sensor and then measure the acceleration values. And so I have my data table set up here that I'm going to plot my underlying equation that I was just talking about. I'm going to set up then M2G with all these different values as my dependent variable that goes on the y-axis. My independent variable is going to be those acceleration values that I obtained. And again, my slope should be the total mass of the system, M1 plus M2. And although we are changing the mass of M1 and M2, the total remain the same, which means our slope should remain the same. Now, you can see here I was getting points off this best fit line, not using the data points, because we got to make sure we use 2 points on the line. However, after plotting this and scaling it, I would use Desmos instead of just plotting this using a manual rise over run. I would just plot this data in Desmos and allow Desmos to calculate the slope of a best fit line. It's just less error prone approach. And then what we're going to do with that is get the slope, which I got to be 0.79. And because I know the slope of 0.79 is equal to the system mass, I can then compare that to what I would get if I put all that stuff on a scale. Okay, so then I did put everything on a scale and got 0.78. And I'd be like, good job, you're the best. No, you're the best with all my teammates. I hope this helps. Please let me know if you have any questions.